So shall we give a couple of minutes or should I start?
You can begin. Thank you.
Right. Thank you. Good morning, all. This is Paul Counts. I think today's topic is AI in ASIC and SOC verification. So we're going to see how AI is transforming and also helping in coverage closure, in debug, and in generating the new test cases. So what are the design verification challenges we have today? So importantly, we have huge design specs, we have a huge verification environments, we have a huge coverage closure to be done. So this requires a huge amount of tests to be run at IP level, at subsystem level, and at SOC level, system on chip level. So our challenge is to hit the complete functional coverage, use cases, and hit the complete code coverage. So what we analyze normally is what we have hit and what we have not hit. So with the increasing in the complexity, most of the conditions, what we want to really hit doesn't happen automatically. We need to feedback, we need to write some test cases, we need to change the constraints at different levels. So this is a big complexity design verification challenges we all as engineers face. I think there are different challenges at IP level, and there are different challenges at subsystem level, and there are different challenges at SOC level. At IP level, as we all know, the sign-off criteria is we have to have 100% functional coverage, 100% code coverage, and all the stress cases needs to be hit. And when we move on to the subsystem level, we are normally giving more importance to the use cases, and we are more focusing on the toggle coverage of the interacting IPs where it is supposed to be hitting. And then as we go on to the SOC level, it's morely use cases and few important test cases, end-to-end data paths, clock resets, memory, and different data paths, mainly when it comes up. So this is the major design verification challenges we have today. So what are the coverage problems we have? We have a lot of coverages written today, but are we hitting it? There are multiple problems there that, first of all the coverages should be correct and it should be hit in the right way. There should not be any false coverages. And whatever is hit has to be analyzed. And we also have to make sure we hit the functional coverage in an effective way and in an efficient way. So that is why we need to fine tune the simulation parameters, the constraints, so that we hit the coverages very effectively. So the tuning of simulation. So what happens? So tuning of simulation is, I have taken into consideration adjusting the sequences, adjusting the constraints, sometimes even adjusting the functional coverage. If it doesn't hit, it becomes illegal bins. We adjust the real functional coverage so that it is actually targeting the design specifications. So we have to tune the simulations in order to hit the correct functional coverage and to hit on the focus areas at the appropriate levels, at IP level, at subsystem level, and at the system on chip level. So one example I have taken here just to illustrate the importance of AI. And in that AI, I have taken a classification of ML just to start with. The simulation environment here, if you really see in the example, is we have design under the test, we have the random knobs, and we have got the ML-based knob settings. And then we have got a simulation output. Then you have got supervised reinforcement learning, so that how this feedback is taken into picture. And this is for one particular design which was done, and how we can manage to hit the functional coverages very effectively. So here I have a next slide where it explains more in detail, but ML plays a very important role to analyze the functional coverage and to analyze the constraints and to bridge the gap between the functional coverage model and the stimulus what we are generating. Because most of the time we have seen in practice that we run a lot of test cases which are hitting the same coverage. There is a redundancy in the amount of test cases what it runs. So we want to make sure the LSF or in any of the servers, the time, all that is used, the resources are used effectively to hit the correct areas in the design and to ensure the coverages keep improving and we are not stuck in the same seeds or same areas it is hitting. So this is where this architecture comes into picture, so that when MLRL based knob settings, like you can make sure this is already hit, and for the next test or the next seed, it will always be not be hitting the same areas. So simulation flow using machine learning, right? Input to the simulation environment are random input configuration, as we know normally, without if you are using. So if you have a certain amount of ML, then what happens? We know what is happening in the output in the functional coverage model, and then we can feed it back and then ensure that this will not repeat. And this is a system, and many people are already starting to use, and this is part of different tool sets. But this is the concept and theory behind it. So output is fed, and then your constraints, your sequences are fine-tuned using this ML algorithm to hit the correct areas. This is a very good slide where everything is clearly put. So here you can see there's a virtual sequence 1 to virtual sequences n, and there's a constraint solver, right? And then there is a virtual sequencer, and this is a normal UVM environment. I think every one of us knows the agent and then duty. And from UVM environment, you have standard environments always we have used, right? We have got sequencer, driver, monitor, virtual sequencer, tests, environments. So what we are focusing on is from the DUT, we have the UVM environment, which drives the DUT. And from the DUT, you collect the coverage. It can be from the input stimulus, it can be from output stimulus, it can be from part of the DUT configurations, it can be from many different places. We collect the coverage, and then that is fed as one input to the ML engine. Here you can clearly see that is fed to the ML engine. And this ML engine also gets the inputs from the constraint solver of the previous generated test case. And this combined with the algorithms, it creates a different constraints for the next set of stimulus, which is going into the agents and then into the DUT. So this is the feedback loop, what we are going to focus. And this has helped a lot in achieving the functional coverage closure faster. And it will also help in ensuring that we are not running the same seeds, same scenarios, same focus areas again and again. So this is the relationship. ML engine is the relationship between the coverage obtained and the input stimulus. So benefits of ML-based coverage closure: optimizes the stimulus created, it reduces the verification cost. As we are becoming more and more streamlined, and it hits the functional coverage faster and in an efficient way, the verification cost reduces. It also uncovers bugs. Sometimes we don't have time to hit everything. Because of the effective way, it can uncover the bugs, corner cases. It reduces the number of iterations for the coverage convergence. It reaches the goal faster in the matter of interaction. In this section, I have taken to explain what is artificial intelligence, not everything, but a very basic concepts of what is artificial intelligence and how it is relating to different aspects of ASIC and SOC verification. AI, in simple, is a simulation of human intelligence processes by machines, particularly computer systems. Specific AI applications include expert systems, natural language processing, speech recognition, facial recognition, mission vision. A lot of applications are there. But in simple, artificial intelligence or AI is a simulation of human intelligence processes by machines, particularly computer systems. And this is very widely defined. What is the purpose of AI? In general, in the top level, It aids human capabilities and helps to make advanced decisions with far-reaching consequences. AI enables processes efficiencies, automates resource-heavy tasks, and makes business prediction based on the real data rather than instinctive feelings. We have a lot of data, and it processes the data, and basically this is all algorithms. It's all algorithms, right? It helps, it takes the data, organizes it, understands it, and then helps us to solve a particular problem. Applications of AI. In general, it helps us to searching within the data, optimizing the search to give the most relevant results. We have seen this in the Google using it for long. We have seen Netflix giving the next movie correctly, or any other things. So there's a lot of applications of AI. Logic chains for if-then reasoning, then it can be applied to execute a string of commands based on the parameters. Pattern detection to identify significant patterns in large set for unique results. In the end, we will see how this can be used in our debug scenario. How we can use AI in the debug, we can see it in the examples in the future. Applied probabilistic models for predicting the future outcomes. Machine learning, if you really see, is just one branch of AI and computer science, which focuses on the use of data and algorithms. AI is very vast, and machine learning is one aspect of it. And it imitates the way humans learn by gradually improving its accuracy. This is what an example I gave before coming here is how the machine learning algorithms learns from the coverage model and then the constraint model, and each passing test cases, it can keep learning what is happening and it improves. And that is what I'm trying to explain here in the what happens in the machine learning. ML is about predicting the future based on the past. It trains itself. It understands this is how it works based on the algorithms, and then it predicts the future based on the past. It's a program to optimize performance criteria using the sample data. It's a program to optimize performance criteria using the sample data. How machine learning works. Decision process. Machine learning algorithms are used to make a prediction or a classification. There's a decision process. It's nothing but in a simple language, programming language, we do if-else statements, case statements, various branching statements. It's a decision making based on certain conditions. These machine learning algorithms are used to make a prediction or a classification. Error function serves to evaluate the prediction of the model and also the model optimization process. If the model can better match the data points in the training set, then the weights are adjusted to reduce the discrepancy between the known example and the model estimate. It keeps on learning from the past. As the human keeps learning from the experiences, this machine learning model keeps learning as we are train it. Like this, a classic example of this is image recognition. When it starts recognizing certain people, certain behavior, it starts matching it with the previous thing, what has happened. This is already used in the worldwide, in the Facebook, we are matching your identity or matching your phone, and Zoom itself uses it to set the automatic background, right? We can see that. And this is what is the model optimization. Deep learning. So deep learning is a class within the machine learning algorithms in the form of a neural network, Right? It uses a cascade of processing unit layers to extract data characteristics and make predictive assumptions about new data. This is a whole topic in itself. I just wanted to touch upon a few things so that we have the basics of AI, ML, DL, and then we can see the applications of that. So in simple, deep learning is a class of machine learning. Machine learning is a part of AI, and deep learning is a part of a class within the machine learning. It uses a cascade of processing unit layers to extract data characteristics and make predictive assumptions about new data. It is more focused. I have taken two examples. There are many other things, but deep learning in simple are trained by using the large sets of labeled data and neural network architectures that learn features directly from the data without the need for manual feature extraction. So deep learning models are trained by using large sets of labeled data and neural network architectures that learn features directly from the data without the need for manual feature extraction. There are two types normally heavily used. that is convolutional neural networks and recurrent neural networks. So the main difference is, to keep it simple, is convolutional neural networks uses with the input data, and it is mainly used for handling 2D data like images. Mainly, it's like a continuous data, whereas the recurrent neural networks uses a feedback, and it is used in speech recognition, natural language processing, all those type of things. The CNN and RNN are the two parts of deep learning. Now, I've just put this slide here as just to make it complete. What is AI SOC verification? We all know, right? As a process we all know there's a design spec given, and then we have do a verification plan. We have a verification strategy, what we do. Then we do verification plan, and based on the verification plan, we develop the verification environment. From the verification environment, initially we build up the whole UVM environments or SVUVM environments or any other environments, and then we go on writing test cases to hit that functional coverages, code coverages, and hit all the use cases, and to make sure we verify the design against the specifications, right? We can use directed approach, constraint random approach at different phases, and then at the end, all sorts of scenarios are supposed to be hit: use cases, stress cases, corner cases, performance tests. Then there can be legal test, error test. All this has to be done, and this is a snapshot of ASIC verification. We all know. I've just put it here so that I'm connecting the two topics: ASIC and SOC verification and the AI. So what are the problems in design verification? Complex IC designs, multiple IPs working together at SOC level, higher clock speeds, higher connectivity for performances. These are the few verifications. I've already touched on it in the beginning. What are the major problems? But as the complexity increases, as we start buying and integrating the IPs or developing the IPs, there are a huge amount of IPs and subsystem levels integrated. And that is one of the initial problems: high clock speeds, high simulation times. All these we are seeing day in and day out. Now, this is where the two domains, the verification and AI, intersects. And that is what I have just tried to give in the initial few minutes. What is verification? What is AI? And then now let us see what is the role of AI in verification in general as a conceptual level, and then that is the intention of today's. The major time-consuming part of, I've taken one thing as verification, is debugging. We all know, we all build environments, we build test cases, then we debug those test cases to find the problems or the differences between the verification environment and design. And most of the time, there are problems in the design, there are problems in the verification environment, and finally it has to converge. So the debugging takes a lot of time. According to research, it's a lot of time it takes. Maybe up to 70% of the verification project is debugging. So AI can help us debug faster with some new approaches. There are new approaches in the market, like, it can help us to debug faster, and then, it can help us to save that time. So more faster you debug, you are able to get to the root cause of the problems between the design and verification, and we are able to solve the issue, go ahead and get to the sign off. It can reduce the debugging time significantly by emphasizing the area of interest on the large log files. One of the example is, if you have a huge log files, AI-based systems or scripts or whatever we call it as, systems can help us to identify the problems very quickly by analyzing all the log files. So one example I've taken is debug assistant. Let's call it as having an AI ML-based debug assistant. What it does, it minimizes the debug time and helps find bugs faster and early. The shift left we always talk about is finding the bugs early, always reduces the cost and reduces the verification time and helps in the project. So this AI ML, if you build the systems, and there are various things in the domain, it can help us to find the bugs early and faster. It minimizes the human error during verification. It reduces the amount of data that needs to be reviewed. Performance of the system can be dealt easily. So AI, if you really can connect AI systems, AI scripts, if you write, it can help you to debug faster, to analyze faster. Instead of seeing the huge logs, which is worth thousands, 10,000s of lines, this AI ML can help us to analyze quickly and to analyze quickly. Sort of executive summary, and to find the first error, to find to classify what may be the anomaly, what went wrong. This is what is happening, and suddenly what happens, right? This type of things where AI ML can be helpful. So just to give a background, right? What types of bugs we find? We find a lot of bugs, right? There can be basic design code error, there can be bad connectivity, there can be misconstrued requirement, bad test vectors, misconstrued interaction with other blocks, timing issues, complex corner cases. There are different types of bugs, right? We all know, we have all faced it, and we have all fixed it, right? So how, what is a traditional debug flow? Right? If you see, traditionally debug flow is like, I've taken an example, and then we all go through the waveform viewers, we all go through the different waveform viewers, different way of debugging, visualizing the digital signals, and then we are coming to it. So this is a traditional debug flow. But in the AI based systems, let's go to the complexity in debugging. There are a lot of complexity in debugging, right? So if you see this, there are huge amount of IPs connected, there are huge amount of data flowing, there are huge amount of configurations happening. It has to be all related to each other. So this right now we are doing with our expertise, the people-centric expertise, not the system-centric. It's a people-centric. People know the IP blocks, people know the system level blocks, people know the SOC level, and then people-driven, expertise-driven, we debug. And this we have been doing for years together, decades together. The complexity in debugging is due to what? At various levels, right? You have lots of complexities like clock speeds, data throughput, available modes of operation. These are the few things I've just picked up. Tolerance levels, access definitions, external IPs. This is few things I've just picked up so that to highlight the issues in the complexity in the debugging. So why AI, how it helps? It reduces the chance of taking an incorrect assumption for granted. It supports the process of asking the appropriate questions, validates the assumptions based on it's basically a system working than the human expertise. Then you are putting all the expertise into the system, scripts, engines, flows, and then trying to debug, revealing the potential path that might take and otherwise have been neglected. So just one more perspective is like, what are the things for debug? Like, we are always debugging the verification parameters, verification environment parameters, design configuration parameters, coverage results, what is happening. All these things are the play or inputs for debugging in normal system. Like, this is the system in the traditional way we take it. So AI helps to put it all together in a context and help us to debug faster. So what are the advantages with the AI approach? It accelerates. I've not taken any specific tool or specific things what's available, but there are a lot of tools available. But in general, I've taken, because it's a tutorial, in general, it accelerates the debug time for a broad range of complexity bug types, ensuring huge resource saving and time to market advantage. Improves design and verification quality over the coverage assessment through visibility into verification scenarios. Extends debug for large-scale system verification on emulation, tracking down the complex issues without the need for resimulation while working cohesively with the existing debug and simulation environments. So the AI can be working as a different part of the tool, part of the flows, or your own engines, or anyway, as a part of the whole ecosystem, it will help us to track down the bug faster, shift left earlier in this way. So let us also see the role in the coverage analysis. Coverage is used for maximizing the accuracy of the testing of the design, right? We have functional coverage, we have code coverage, we have got different parameters, different things for as a sign-off parameters. So what is the coverage analysis? At present, the manual analysis of the coverage database is performed by design and verification engineers towards the closing of the phase. At different phases we do. We do predominantly in the end, but we also start analyzing in the very early stages to catch some differences in the environment. We see how the quality of the environment, how the quality of the test cases, quality of the use cases, quality of what we are doing. We start analyzing at different phases for different purposes, but towards the end of the verification projects, it is mainly driven for a sign off. Analyzing the coverage becomes very, very important, and that is how the coverage analysis becomes the critical component before we say, okay, we can go for a tape out. And that's why we keep reporting different parameters to the top management: code coverage, functional coverage, and within the code coverage, sometimes we want toggle coverage if it's at subsystem level or at the SOC level. So we keep reporting, and that is how we do. And normally it is manual, right? If you implement an AI/ML algorithm, would help in saving considerable amount of manual work, because this can correlate according to the design, according to the industry specific, and then help you to analyze the coverage analysis, develop the test plans, and meet the goals for the schedules. So this will help us. Like, it can be a point tool, it can be an analysis tool, which will help you to guide towards achieving the coverage goals faster. So let's go through this here step by step. You have in the normal flow, in the existing flow, or we can say with the previous to AI. In general, some people are already using it, some people will use it. So let's consider as a previous flow. You normally run the test with the different input configurations, data paths, all this. Coverage data, generate the coverage database. After the coverage database is done by running the thing, you do the manual analysis of the coverage database by RTL designers, verification owners, sometimes managers, sometimes project managers, whoever is it. But basically, it will be by designers and verification engineers and verification owners, basically. And then what you do is normally you end up modifying the sequences, modifying the scenarios, correcting the functional coverage model itself sometimes, or correcting the verification plan itself sometimes. And also sometimes it leads that certain things are not achievable in this particular verification environment. And so we end up modifying different ways. Maybe we may be modifying the spec also sometimes. We may be modifying the verification plan, verification strategy, or certain things can be done later. But these are all done in the existing flow by manual analysis of the coverage. Now, if you, in the second part of this slide, we can see if you include apply ML to analyze the coverage database, what happens is you can run tests with the different configurations. You can generate coverage database. You can apply ML to analyze coverage databases. And then it can help up to a certain level. I don't say fully, but in the future, it can be fully. It can be everyone's dream is to have a single click solution and it can give you 100% coverage. But yes, but in theory, in practice, there'll be some manual intervention required, but it can be reduced. Manual analysis can be reduced, and effectiveness can be improved, productivity can improve, and innovation can improve, So this is what it says. It modifies the sequences. So when you see ML, it definitely saves a lot of time and energy when ML engine sits here to analyze and to modify sequences, scenarios to improve the coverage percentage. Okay. So I've just taken from general thing, what do you do? The huge, one of the examples of traditional versus modern debugging processes. Right? So you have a huge flows from log files normally. And then you write it down, and then you do the waveform viewer, and this is our traditional flow. But in the latest flow, if you are using the AI/ML system, you can get the logs to be read by AI/ML engines and then given it to you in a graphical processes. So what happens is you are able to visually see what is happening, and you are able to come to a conclusion that this is where the bugs are. This is where your real issues. This is where or there are other aspects also. You can also see what sort of scenarios are being run. But just by seeing the log, sometimes it becomes difficult what is happening in the different interfaces. For example, if the system on chip has got 5 different interfaces, one may be APB, one may be AXI, one may be Ethernet, one side may be USB, one side may be and something else, right? What is happening in each interfaces at given time? It's very difficult to find out using the different logs. But if you can put it in a graphical format, then pull it all together and put it in the thing from analyzing from the AI/ML engine, and then put it into a graphical format, I think this will help us to analyze what is the scenarios happening, and also it will help us in the debugging process. So I've just put one more thing in the debugging, what happens, right? Debugging is a time-consuming process. I've just dealt a couple of times before. It's a data sets to analyze without proper tools, right? It's a huge data sets you have got. A lot of questions, assumptions, answers you have got to do, right? You have got a lot of questions, you've got a lot of assumptions. Basically, when you're debugging, you go through the set of questions and set of answers. Where can be the problem, right? So debugging, like, if you find something is not working, first of all, we go through, if you have got 5 blocks in series, we go on identifying, we try to say, okay, sort of identify the scope where the problem may be. Is it the problem in the first module or second module or third module or a fourth module? Like, this is the right questions we keep asking, right? If you see what is the debugging process, it's a series of questions and assumptions and answers and conclusions. So you're trying to pinpoint or the focus on the area where there's a real bug happen. Now there are different environments, we can come up with the different ways of debugging information, debugging strategy to isolate the problem and to debug it faster. So we can see here in the traditional debug flow and in the AI/ML flow how we can try to ask different questions and to try to find the bug found. I tried to put this here so that to highlight how asking the right questions and right answers can lead to isolate the problem faster and to find the bug quickly. So here you can see very clearly you have asked some question. If it's the wrong question, then answer is there, and then you have different question you ask, then answer is there, and then you go through it, and then you find the dead path. Then it's the wrong path, then you come to the question again. So basically in the debugging, this just tries to put it in a way what we do in the day-to-day activity, right? We say if you have 5 different interfaces, we say, oh, the problem may be there in the configurations, or maybe problem may be there in the data path, or problem may be there in some of the processing engines or the processing elements. So we try to ask the question and go down the different paths, and this may lead to a lot of time-consuming efforts. So if you go to the right question and if you ask the right question and right answers, you can find the bug or isolate the issues and can be found. And this if you put it into the ML flow and if you try to make it an intelligent system, this can save a lot of time. Yes, so I have finally tried to highlight even the AI pitfalls, like, what sometimes we all expect everything. If you put an AI engine, everything will, on the one click, you can have the functional coverage closure, or you can have the debugging done very quickly, or, it can be all like idealistic. But AI is not an answer to everything, but it helps, it accelerates, it empowers you, it enables you, but it is not everything. It is not a solution, single click solution, quick solution for everything. That is why I also wanted to list it, like, what are the pitfalls. It can be a cold start, expecting AI to do all the work. That's one of the pitfalls. Sometimes people say, okay, once you have AI engine, you can do everything very faster. And we need to have right frameworks, meaningless metrics, right? Setting and forgetting, missing the big picture. Sometimes, we may be, there should be a human intervention required, right? Trapping the users in the bubble. Sometimes if it's just we are using only the systems, failing to optimize the processing time, not valuing the privacy and consent of employees, or not upskilling your term, right? So just to highlight and close, the AI in SOC, ASIC and SOC verification, it's a work in progress. It's happening in the different fields. So we have started seeing it in the coverage closure. We have seen some example. We have started seeing it in the debug. We have started seeing it in the generating the new test cases also automatically up to certain level to close the coverage. And it is beginning to happen in different ways. Just to automate what could be automated, we can use the AI, ML, DL algorithms to automate and accelerate and help in the ASIC SOC verification. So with this, I open for questions. Can stop sharing. Yes. So anyone has some questions, please feel free to ask.
Hi, Paul. This is Paul Singh from Unicare. How are you?
Good, good, good.
Yeah, actually, maybe you wish to add two things. One, that AI is helping a lot in TLM modeling also because you can find a lot of use cases in the TLM, and it's called long-term short memory for the gate level simulation using machine learning approaches.
Yes, I agree.
And
I
we,
agree.
we also tried on the main thing with deep learning is if it do mistake, it keep on doing mistake. It never learns from mistake unless the software try to embase that.
Yes, yes. That is why in the pitfalls I put sometime, you know, it can get into the closed loop, and without the human intervention, it gets stuck there.
Yeah, because
You're
you need
right.
a lot of data from the your customer use cases rather than your use cases because they have more visibility at the system level rather than the SOC or API level
Yes,
to
yes,
identify the corner cases.
yes.
But it's a
So
good
definitely
presentation.
this can help us. This can help us, but this is not the at least at this stage what we can say. This has not evolved to a complete, very intelligent system, but it can help us. But yes, you're right that we need to intervene and we need to make sure that some of the pitfalls we should be aware of it.
So one question you may wish to ignore: which tool you find best? An office mentor or guidance for this thing?
No, I think I better not answer that. That's why I kept it as neutral as
Okay,
possible.
take it easy. Just joke.
Yes, just to keep it general and as a general topic. This is the intention was to make sure to highlight that AI is being used at different levels and
Hmm.
different tools and different combination of tools. And I've seen in the industry there are a lot of tools, different tools. Right, but majority of the area I find is coverage closure, debug, right, testing the new test cases, various point tools and integrated. And all in all, I think end to end it is helping us to accelerate, helping us to find the bugs faster, earlier. But I think, yeah, everyone is at different stages.
Yeah, the I can say in my experience from past using 4 years, the best use case is FSM coverage and multi-level cache memories. That's the best
Yes,
for the AI ML.
yes,
In which
yes.
the even the more random is also not helping.
Yes, I think more random. You're right, because when the complexity of the chip increases, randomness. If you really see all our experiences, randomness will help at the IP level, right? And when there is
Yes,
a certain coverage space, when we go up to the SOC level, what happens when the scenarios are increasing huge amount of scenarios and software hardware interaction is more, then the arcs become too much, and that is where
correct.
I think that constraining is important. And then that is where it is going towards the use case. If you really see at top level, I know very few companies, they are using functional coverage, but they are not using completely random, they are using very constrained random, like use cases approach is more.
Hmm. Totally agree. Thanks, Paul.
Yes, yes, thank you for a very good question and insight. Yes, there is a question in the from. Yes. How should we make sure the AIML automation is bug free? What should be the metrics of verifying the AI model state graphics? Yes, I think it depends upon the tool sets. And the AIML automation, I think that's also evolving. There is some issues there. So that is why I think he addressed it. We should be always in the sync, whether we are diverting or we are getting stuck in the loop, or we have to make sure definitely that we have to balance between our focus area of verification and the AI tools what we are using. Are we getting into a loop which is not helpful in our real verification of the focus? Then that's what I can say at this point. Okay, there is one more question. Can you please provide a clear example of what should be the data set used to train a neural network? So I think one example I can say is, I always say is like, between the coverage output, right? Coverage database, and then that can be used to train the sequencer, how to generate that. But actually there should be a lot of relations, because we all know that coverage language is different than the constraint language. So this is one of the problems, and then how it maps it, and that is what AI/ML engine all is about. That's one thing. And there is one more question: is the learning happening dynamically during the regression, or is it post-processing? No, it can happen dynamically also. It can happen post-processing also. It all depends upon what systems you are using. So post-processing is then you are hitting the next seed in the next running, but dynamically you can also tweak it. So there are different engines in the industry which is using both dynamically also post-processing also. Okay, there's one more question. To apply ML in your own project, do you train it from your own past projects? What are the requirements to get the learning system to actually work for a certain project? It's a very good question, because for the derivative chips, I think your previous data sets will be really helpful, because you'll have a handset of test which has really helped you to achieve the functional coverages faster. But it also depends upon how intelligent is your AI engine, how much it's able to learn from it, and how much it is able to adapt. But having the old data projects is very important sometimes, because you have achieved 100% coverage in the data, and what is that changing and where it can be focused. Yes, it is possible, but it also depends upon the engine and then how we can tweak it. Right, there's one more question. What if the coverage is not obtained for a group of inputs, but for a sequence of groups of inputs? How do you build that training database in this case? Sequence of groups of inputs. Yes, I think there's a different layers are built, but that's my understanding. You can also go to the complexity levels, layers. Different layers can be built. It's not only on the static of one group of inputs. It can be layers of groups, and layers of sequences can be built, but it becomes complex and complex over the period of time. I think very good questions. Excellent. And if there are no more questions, I think we can break, and then I think we can take a few minutes break before the next session. So thank you all. Okay, how can we evaluate tools? That's a very interesting question. I think in my past experiences, we have to take a project, we have to take a particular type of domain level project, we have to take a typical levels, whether it is IP level, subsystem level, or a SOC level, and then you try to evaluate, because there may be a sweet spots for different type of tools. So you need to know what is your objective, and then you map it and see what tools fits your need well. And that's very important, because what are your project needs, at what spots you are in, IP level, subsystem level, or top level, and then where are your problems and which tools have effects. And that is how is my experience. And of course, talking to the vendors, they'll always tell their part, and it's always the collaboration. All right, thank you very much, I think, for a very good questions. And I think we can take few minutes break before we start the new one. Really appreciate your time. Thank you very much.